are in listen-only mode.
Okay, and we're live.
Greetings. This is Howard Wigg, State Energy Office, Honolulu, Hawaii. Welcome to Webinar 2 of the 2015 IECC International Energy Conservation Code. This is the second in a series of webinars. We just had one on the Tropical Code a little while ago, and in the next 3 days we will have 3 separate commercial building codes. Again, my name is Howard Wigg. I have been with the Hawaii State Energy Office for 30-odd years and have participated in energy code development ever since the first energy codes came into being in the early 1980s, and have followed that progress and indeed led that progress through the years to the point where we are now at IECC 2015. Today we'll be looking at fully conditioned homes. That is where you have a central air conditioner, or every room in the home is air conditioned. Joining me is Eric Makala, who is a very tall presence in the energy code world. There are many, many national code conferences where we decide the next iteration of energy codes, and Eric is always there, front and center. I should mention that I am always there also, that I'm not nearly as tall a presence. I specialize in the tropical aspect of the energy codes, and Eric specializes in everything. He is a consultant to, let's see, Bahrain, Dubai, and many, many other states, and more relevantly, a consultant to Hawaii today. So the energy codes, as we will see, is a very, very important component to the Hawaii Clean Energy Initiative, where we have a goal of 100% clean energy for electrical production by the year 2045. And the energy codes are a really, really big step towards achieving that. So without further ado, let me turn it over to Eric, who first will poll you as to who you are and then instruct you as to how to dial in your questions as you're going along. Take it away, Eric.
Thank you, Howard, and welcome everyone. Glad you could make it, and it looks like we have a good turnout today. So Howard kind of told you a little bit about himself and myself, and I want to add we've also done work in the Commonwealth and Northern Mariana Islands, Guam, Saipan, which is in CNMI, and also in Fiji, working with them on energy codes, and has coordinated pretty closely with Howard on the Tropical Energy Code over the years. So we've done quite a bit of analysis in the development of the 2015 IECC for Hawaii to make sure that we could produce amendments that made sense for the state, because the code is really developed as a mainland code, and it really doesn't take into account a lot of the things that work well in tropical zones. So what we're going to be talking about today is how we're talking about are really fully conditioned buildings, fully cooled buildings. But before we get into that, we want to find out who's on the webinar today. So we're going to go ahead and launch a poll and kind of allow you to identify yourself. And so I'm going to go ahead and launch this, and if you can take a minute or two to see which category you fit into which category you fit into, and then so Howard and I will have a better sense of who our target audience actually is. So we'll give you about a minute to answer this, and then we'll go ahead and get moving with the rest of the webinar. Okay, another 20 seconds or so, and I'll go ahead and shut this down. Actually, it looks like there's no more data coming in, so I'm going to go ahead and close this now. And then I'll go ahead and share the results with everyone. And it looks like Howard, about the same what we had on the tropical zone. We have mostly other, which we've classified as material manufacturers, consultants, people that don't fit neatly into the building official, builder, architect, or engineer category. We have several engineers, several architects, and building official, plan review and inspector, and about 4% builder. So we had more builders, I think, on the last one, but this is great. It's a good mix. So with that, let's go ahead and move on with the presentation. So what we're going to do is we're going to spend the next hour presenting material on fully conditioned buildings and the residential requirements of those buildings. At the end of that time, we'll go ahead and take questions. And the way we're going to do this is we're going to ask you to email in the questions as you think of them, and then Howard and I will go ahead and take the questions at the end of the session. So if you could email the questions into the email address on the screen, and we are going to bring this up again at the end of the presentation too. So if you don't get a chance to write it down now, because it's not in your slide presentation, Jolynn Green at cadmusgroup.com. So I'll give you a few seconds to go ahead and write this down. But again, we will bring it up again at the end of the presentation. So if you didn't get it right, at least you'll have the opportunity to see it again. So Jolynn Green at cadmusgroup.com. Again, go ahead and send your questions in, and we'll answer them all at the end of the presentation. So with that, I believe, Howard, I'm going to turn this over to you to kind of lay the groundwork for what we're going to be talking about today and what's been happening in Hawaii for the last 2 years now, I guess. So.
Sure, absolutely. I should have mentioned in introducing Eric that he is now a principal with the Cadmus Group. That is a major engineering firm worldwide. He used to have his own outfit, but Cadmus Group thought he was so good that they bought him out. And for myself, I am also president of the Hawaii chapter of the Illuminating Engineering Society and the International Dark Skies Association. So what we've been doing in the last few years is looking at the mainland code and asking ourselves, are all the provisions applicable to Hawaii's unique climate? The answer has been no. And for those of you who attended the tropical code session, you saw where we took advantage of the fact that we now have a whole separate tropical climate zone, which pretty well boils down to Hawaii. And that gave us a blank slate on which to write whatever we wanted to write. And if you're familiar with mainland codes, we made some pretty significant changes there. And also, there are other codes, one being the National Green Building Standard, which is promulgated by the NAHB, National Home Builders Association. And I was instrumental in developing the 2015 version of that. And we inserted the Hawaii or tropical climate zone into that code as well, which brings me to the fact that this code is the minimal code. There are several beyond codes out there for use on a voluntary basis. That includes ASHRAE's 189 and ICC's International Green Conservation Code. And those go usually about 10%, maybe closer to 20% above this minimal code. And word on how Hawaii develops its codes, and for those of you who sat on the tropical code, excuse for some repetition here, there was formed in 2007 the Hawaii Building Code Council. And I'm the energy chair on that council, and we meet once a month, and Neighbor Island people fly in, and around that table are the fire code people, the plumbing code people, electrical, mechanical, and so forth. And the legislature created this council so that we could all communicate with one another, and hopefully all the counties could be on the same page in their code development. That said, the law that created the council appropriated funds to hire an administrative director, because this is a really, really complex process. And we did not get funding that year, and we have not gotten any funding the subsequent years, such that we are way behind on our code development cycle. So in this case, we're going to jump all the way from IECC 2006 to 2015, whereas ideally you update your codes every 3 years according to the national cycles. Why update codes all the time? Well, you're familiar with Moore's Law. There was a Dr. Moore, who was one of the founders of Intel Corporation, who back in 1971, looking at the development of computers, calculated that they would double in capacity and halve in size every 2 years. Well, he was pretty well right on the button. If you have one of those fancy watches on your wrist, you have more computing power in that than did the U.S. military during the Korean War. A sort of a wise guy from Intel Corporation recently calculated that if a 1971 Volkswagen bus had undergone the same revolutionary improvements as have computers, that bus could go 200,000 miles an hour, would get 3 million miles to the gallon, and cost 4 cents. Such is the improvement in computers. The rest of the building technologies have not improved at that rate, but they have improved very, very rapidly, as we will see as we go through the program. And the purpose of updating the codes every 3 years is simply to keep up with those rapid improvements, because we can make homes more efficient, safer, better, everything by following new codes. Let's go to the next slide, please. Structure. You will find just about any code under the book has this type of structure because it makes sense. First, scope and administration. That defines what this code is going to cover and who's going to be covering it. Without that, you have no mission, you have no direction. Definitions. Every profession, doctors, lawyers, and code officials have their own set of words, vocabularies, and very often those vocabularies are very specialized. That's what these definitions are all about, so we know what we are talking about. General requirements. The biggest portion of this section are the climate zones that each county in the nation fall into. There's 8 climate zones going from southern Florida to northern Alaska. Actually, now there's 9 with the tropical code in there. And in my unbiased opinion, the most important part of this section is the first section, which defines the tropical climate zone. Next, energy efficiency. And this is where you get into the meat and potatoes of the code. You start with the envelope, the walls, windows, roofs. Then you go into the HVAC sections. In this case, it's just conditioning, not heating, plus water heating. And finally, you get into lighting and electrical. And here's something new. Existing buildings. The codes always have had certain provisions for renovations, but now this section is a section unto itself. And the most important section of that we found, based on a lot of input, is the roofing section. And we'll get into the details there. When you are re-roofing, now you must follow certain specific provisions. And finally, the reference standards. This code refers to a number of other standards, and those are defined in that section. So I just went through commercial. The exact same structure applies to residential. Next slide, please. Energy savings. Codes, energy codes are the gift that keep on giving, because compared to IECC 2006, IECC 2015 will be 30, 31, 32% more efficient. So that the buildings built in accord with that in year one will save X. But that's not all. Those buildings in year one are going to continue to save in year 2, 3, 4, 5, and we project it out to 20 years. Why 20 years? Because certain aspects of that building, such as the equipment inside of it, are not going to last for 20 years, but the envelope is going to last for 30, 40, 50, maybe even more years. So we took an average of 20. So the year one savings going out over time is X times 20. That's pretty good savings. But wait a minute, there's more. The next year, that code will be followed again. And for a 20-year period, you take that year two savings out for 19 years. And the third year, you take that savings out for 18 years and so forth. The end result is cumulative savings. All of those savings put together. And the first column is residential, next commercial, finally orange on the right, cumulative savings for both building types. Look at just 2016. This would assume that the code was put into place in 2016, which it's not. Incidentally, sidebar, when will 2015 be adopted? I'm hoping that the adoption process will start late this year and be completed in 2017. Code adoption is always slower than we would like. But look at the savings in year one, 160 gigawatts. What in the world is a gigawatt? Well, you take a watt, we all know what that is. You have a 60-watt lamp, that's 60 watts. So you multiply 1 watt by 1,000, and you get a kilowatt. Kilo in Greek is 1,000, and that's the way we generally measure electrical consumption. And since you get your electricity bill and it tells you you've used 200 kilowatt hours or whatever, but you take that kilowatt and multiply that by 1,000, and you get megawatts. This is what, say, Hawaiian Electric measures its consumption in. At the, say, the quietest time of the morning, 3 o'clock in the morning, they might be drawing, say, 600 or 500 megawatts statewide. And at the peak of the day, in this case, it'd be around 7 p.m., you might draw 1,100 megawatt. And little sidebar there. Oh no, I'll go into the peak savings later. But then you have your megawatts, multiply that by 1,000, and you've got gigawatts. And if you translate that 100 or just 1 gigawatt hour, you can do the math starting at, say, 25 cents a kilowatt hour. In the first year, you're going to be saving 40 million, that's an M, $40 million based on 25 cents a kilowatt hour. You can see, and then you multiply that over 20 years cumulative, we are talking some very, very, very big numbers. This is a major step towards achieving the Hawaii Clean Energy Initiative. Next slide, please. Residential provisions. What is a residence? Excellent question. We normally think of single-family homes, but wait, there's townhouses. Those count as residences. But wait, there's more. Any apartment building up to 3 stories also counts as a residence. That's the way we do the cutoff now. And a lot of code provisions go around that, because if you do 4 stories or more, you need an elevator. So what if you have, say, a 3-story building with retail shops on the first floor, offices on the second, and residence on the third? First 2 floors count as commercial buildings, third floor counts as a residential space. We are looking to create a whole new category of building called multifamily, which would be small apartment buildings all the way up to the new high-rises that are going up in Kaka'ako. Next slide, please. Jen Ball. Okay, we start with, as I indicated, the envelope in any code, the roofs, walls, windows. Why? Because the way you construct those has a lot to do with what you put on the interior. The better your envelope, the less heat is going to enter the building, so you can downsize your air conditioning or have no air conditioning at all. Then you get into HVAC and you size accordingly. And in the case of, say, single-family residences, you could either do a series of split systems or one central air conditioning system. And then you get into lighting and electrical, and I'll have quite a bit to say about electrical or lighting later. But the less horsepower, let's say, you have in the building, because you've designed the envelope very efficiently, the less your electrical load. So you design your electrical distribution system accordingly. Next slide, please.
And I think this is me, right? Yeah. Yes. Okay. Thanks, Howard. So Howard laid the groundwork for what kind of the process for code development and where we are right now. And I do have to correct Howard on one thing. I'm not a principal at Cadmus Group. I'm a senior associate. So I just wanted to make sure. Also, you may not know I'm actually broadcasting out of Boise, Idaho. So that's something that I don't think we mentioned on the tropical zone. Not that it makes a difference, but it is. I just figured I'd bring that up. So there's multiple compliance options available to you on the prescriptive or on the for the residential energy codes, and we just wrapped up a webinar for the tropical zone, and which is for a building that's 50% condition, and there's fewer requirements on that. When we start looking at buildings that are fully conditioned, so we're air conditioning every room, and we're putting larger systems on there. There's really 4 different options for you for compliance. One is a prescriptive option, and prescriptive means it's a very simple, straightforward approach. We'll see you have a list of insulation requirements you have to meet, and there's really no trade-offs that are in the code. We actually added some that we'll talk about that, but it's there's no trade-offs permitted. You don't need any tools. You can just show that you've complied prescriptively on the plans and you're done with it. And it's typically been the preferred method for energy code compliance in Hawaii. Then there's something called the total UA alternative, and this is for a building where you have a project and maybe you can't get as much insulation in the walls, but you can put more in the ceiling, or so parts of your building don't comply with the prescriptive requirements of the code, but parts of the building over comply with the prescriptive requirements of the code. So if you look at the entire building on average, complies with the energy code. So a UA, U value times the area, is a prescriptive method for doing trade-offs with levels of efficiency in the building. And this is where the U.S. Department of Energy res check comes in, because it's designed around the UA compliance approach in the code. You have the performance-based approach, and performance-based is essentially doing computer simulation, applying Hawaii weather data on a proposed building, and we'll talk a little bit about that later on in this webinar. It's the most sophisticated method of complying with the code because it's all done via computer simulation, and you actually calculate out how much it's going to cost you to operate your proposed building, And if that is less than or equal to a building that complies minimally with the code requirements, then you've complied with the code. And again, we'll talk about that in a little bit later. Then we have something new called the Energy Rating Index. And the Energy Rating Index is a home energy rating system type of an approach that basically allows you to rate your home, and based on that rating, you comply with the energy code. This is brand new in the code. It's going through some changes and tweaks and modifications in the code development process right now, but and it may or may not be a useful tool or useful method in Hawaii to do this, but it'll be an option. So with that, right now what we want to do is go ahead and jump into the prescriptive requirements of the energy code.
Eric,
yes,
let me jump in just with a brief comment. Eric and I did statewide training last November, where we went everywhere and did training on this code. And when we were on Oahu, we asked people, how many of you are going to comply via the prescriptive method, which would apply best to centrally conditioned homes? And about 75% of the people raised their hand. The remaining would do tropical code. Then when we got to the neighbor islands, those numbers were reversed. About 75% of the people said that now that the tropical code option is available, they will do that. Why? Because on the neighbor islands, you've got a lot more room, and the tropical code home works a whole lot better when you've got some privacy and you've got a nice lawn in front of you. Of course, most of our new homes are of necessity on small lots. So again, the prescriptive code will apply most on this island especially. Mm-hmm. Go ahead, Eric.
Great, thanks, Howard. So what we're going to want to look at now is the prescriptive approach, and again, it's a simple, easy process for doing this. And I'm going to grab a highlighter over here to kind of talk a little bit about this. So when we did the analysis for the state of Hawaii, we noticed there were two parts of the building that really impact energy use for residential buildings. One is the roof assembly, one is the window assembly. It's not that walls aren't important, it's just that they typically don't impact energy use as much as your roof, which is essentially a large solar collector that it's very difficult to shade, and your glass, which is in most hot or warm tropic climates, a lot of your loads come through your windows. So from a energy code standpoint, for one thing, you can build a 100% glass house. The code, there's no glazing restrictions on the building, and you could actually build a glass cube. The only thing is you can't be modest to live in that house, but other than that, you can go for it. There's no fenestration U factor requirement, so you can essentially put in single pane glass, but the glass all has to be fairly, oops, that just kind of wiped it out. Fairly efficient, 0.25 solar heat gain coefficient, and the solar heat gain coefficient is just the amount of solar gain that is allowed to pass through the window. So what a 0.25 means is that the glass actually allows 25% of the solar gain to pass through, which is the part that brings heat into the building and either reflects off or absorbs and re-radiates it back to the outside atmosphere 75%. So 0.25 is a fairly low solar heat gain coefficient, and it's really designed for hotter climates. You can see the ceiling insulation requirement is an R30. Now there are trade-offs that we're going to look at. We have a points-based option that we developed for Hawaii. It's the only place right now it's really being used in the U.S. So we developed it specifically for Hawaii to allow you to do prescriptive trade-offs. So if you go straight prescriptive, then it's going to be R30 insulation in the ceiling. Wood-framed wall, I do want to emphasize this is wood-frame wall insulation is an R13. If you're using metal frame walls, there's actually a trade-off that we've put into the code too on the points-based option, because right now for the code, as Howard mentioned, was developed basically for the mainland, and it doesn't work that well for tropical zones. So we modified it to make it work better. So wood-framed insulation R13, because some insulation is always a good idea for fully conditioned buildings. For metal frame walls, though, the requirement is actually to use R13 between the studs and then foam board insulation over the face of the framing. But what we found out in Hawaii is that foam board insulation is really not that effective. It doesn't get you that a big bang for the buck, and it's quite expensive to put on. So we came up with an option for eliminating that, kind of a prescriptive trade-off. You'll notice floors, there really aren't any requirements for insulating floors. Because there's no heat gain through your floor, whether it be a raised floor or slab on grade. And your slab grade insulation R value is 0 on that too. So it's a fairly straightforward process for complying with the code. And this is just the values you need to comply with. Now what we want to do is get into, get rid of my pointer here, and get into some specific requirements of the code. One of them is above grade walls, and this is the exception down here. This is essentially saying that you can comply and do trade-offs using the section R407 points option. And again, we're going to look at the points option. This is just a prescriptive method for being able to trade off against higher levels of insulation or code levels of insulation. Ultimately, from an efficiency standpoint, you're going to come to the same place from an energy using standpoint in the building. It just gives you a method for trading off without having to use any kind of software. So this basically says that you have to comply with the prescriptive requirements of the code, but you can trade off ceiling insulation and wall insulation using the points option. For glazing, we know that it's important. It doesn't make sense to have low solar heat gain coefficient glass on windows that are out on the lanai, for example, because they're completely shaded and you're not going to get any solar gain on that. So putting in some kind of an optional tray or a method for putting in relatively clear glass made a lot of sense. So you're allowed to actually use an area weighted average solar heat gain coefficient for the glass that you put into the building. So you can put in relatively clear glass again on areas on glazing that are shaded most of the day.
And Eric, I should
Yes.
mention, we even have a special provision for north-facing glazing also.
Yes, actually we do on that. So yeah. Okay, so prescriptive, again, you have a set of prescriptive requirements, fairly straightforward, and then we need to figure out, okay, those are nice, but what happens if we want to, I'm going to call it optimizing our house, and what happens if we want to go ahead and maybe put in more insulation in the ceiling and trade off insulation in the walls or vice versa, however you want to do it. So the points option was developed. We did a lot of analysis. We looked at things that had impact in Hawaii from a feature standpoint, either a negative or positive impact. And we tried to keep this fairly simple. If you go into here to try to comply with walls, for example, and trade off wall insulation for something else, your goal is 0 points. This is what you want to hit, is actually 0 points. And some of the features that you want to trade off are worth 1 point and some are worth -1 point, but ultimately your goal is 0. So if we look at the way the table is structured, first of all, we have our building assemblies on the left column, and then we have standard home points. This is a fully conditioned building. And then we have tropical home points, and we're not gonna look at that from this for this webinar. We're going to be focusing on standard home points. And for example, I want to go ahead and I'm going to go ahead and trade off. Let's see, I need a -1. I want to put R19 roof insulation in my house, and I notice over here that it's a -1 point. So I just need to go down through here now and pick something that is actually a +1 point so that I ultimately become to 0. So my R19 insulation can come down and I can actually put in a higher efficiency air conditioner, for example. So 14 SEER is a minimum, somewhere in the 15.5 roughly. I'd have to do the calculations of 1.071 times the federal minimum SEER. If I put in a slightly higher efficiency piece of equipment, I can actually trade off my roof insulation. Or if what are my other point options down here? Let's say I'm building I'm going to be putting in Energy Star fans in all my rooms, and there are some criteria. You see the footnote 8, there's some criteria on that, and that's worth a point. So I can actually, from an energy saving standpoint, can put in fans, it means I'm reducing the use of my air conditioner, and fans actually save quite a bit of money and energy. So that's an option too. I can actually put in my R13 wall insulation with exterior shading. That's worth a point. So if I shade my wall system, again, I can get 1 point there. That offsets my negative 1 point on here, and I can comply with the code. So again, a prescriptive method for just doing some energy neutral types of trade-offs. Probably one of the biggest areas, though, I think we're going to see the trade-offs done are metal frame walls. And I talked about the fact that the prescriptive table is based on wood framing. So if you do want to trade off for metal frame wall systems, here is a standard prescriptive option for metal frame that's in the code is an R13 between framing plus an R3 continuous insulation. So it's foam board insulation on the outside of my metal stud wall that covers the face of the studs. And that's really the most efficient place to put that. But if I want to get rid of that continuous insulation, which again, we talked about it being fairly cost prohibitive and not really giving you a big impact, you can go with an R13 cavity plus an R0, which is the second row down, and you'll see it's worth a -1 point. And then all I need to do is pick up that point somewhere else. So if I want to put in 90% high efficacy lighting and all Energy Star appliances, for example, I can pick up a point. Or I can come down and put in a ductless air conditioner. If I'm going to do a ductless cooling system in my house, that's worth a point. Or a higher efficiency cooling system. That's worth a point there too. So, or I can go ahead and minimally code compliant wall system is an R13 metal frame with high reflectance walls, because again, you're going to get the same bang for the buck as that foam board insulation. So that's worth 0 points right there. So this gives me, if I put in the high reflectance wall systems, I automatically comply with the code and I'm good to go. This also gives you the option of putting in a KW or greater solar electric as an option. Now you're not necessarily going to save energy in your house with PV, but you do take power off the grid. So ultimately it does impact the power production in Hawaii. So anyway, this is how the points option. Here's the footnotes.
Eric,
yes, go ahead.
Eric, let me jump in on the metal frame walls, because this is very crucial, especially to Oahu. We are unique in the nation on this island in the fact that 75% of all new single-family construction is metal frame. And on the mainland, it's just a tiny percentage. So this got the attention of the National Steel Framing Alliance, headquartered back east, but they sent their president and their consultant down here when this provision first came up, because the national code requires, in addition to the interior wall insulation, I believe it's R5 exterior insulation. And the steel framing folks are quick to point out that that exterior insulation would add about $8,000 to the cost of the home, but given our very mild climate, it would save only 484 kWh a year. And even back then, when a kWh cost 35 cents, your savings was $140. If you divide 140 into 8,000, you will come up with something like a 42-year payback. That doesn't make sense. So we set about having a lot of meetings with them, and we came up with the alternatives of shading the walls or having reflective walls. So again, we're unique in the nation on that. And the military decided to do exterior insulation anyway, because they're subject just to federal laws, and that's here on Oahu. The exterior insulation cost them $13,000 per home, and when the final job was inspected, it was found that the exterior insulation was held to the walls by big metal bolts. Well, guess what? Metal conducts heat. So part of the benefit of that exterior insulation was negated by these big metal bolts. So we're very, very satisfied with the fact that we were able to provide an alternative to the steel framing folks. And again, this is totally unique to Hawaii. Thank you.
Great, thanks, Howard. Okay, so from a footnotes, the footnotes basically explain everything that's in the prescriptive tables, and it gives a criteria for things like radiant barrier, cool roofs, what we mean by Energy Star, energy rated appliance or Energy Star rated appliances, and what appliances we're really looking at there. So it just provides a little bit of a background and sets the criteria in order to be able to take credit for some of these features in the points option. So that's it for the envelope requirements. Now what I want to do is start taking a look at, I should say that's it for the insulation and glazing requirements. Now what we want to take a look at is one more feature that's required in the code. And again, this is for fully conditioned buildings. But what we have found, what the analysis shows is that reduced air leakage in residential and commercial buildings, for that matter, actually can save quite a bit of energy, because if you're cooling the inside of a building and you're fully conditioning that building, you want to keep the cool air in and the hot air out. And so in order to do that, you need to seal up what we consider the building envelope, and that's the parts of the building that surround the area you're cooling. And so that's your roof ceiling assembly, your wall assembly, and your floor assembly. The code now is requiring that you actually do a blower door test. You basically test for maximum air leakage of that building envelope, and you test to something called 5 air changes per hour at 50 Pascal. So you basically depressurize the house, and you measure the difference in pressure between the inside and the outside of the house, and you have to be less than 5 air changes an hour. And if you do that, you've complied with the code. So from a testing standpoint, those of you that haven't seen this, I'll introduce you to the blower door, which is on the right-hand side of the picture. It's essentially a fan system that connects to the entrance into your house, and it's you have a basically vinyl sheathing that covers up the entire doorway with a very large fan. That fan then is large enough to be able to depressurize your house at 50 Pascal. 50 Pascal is the same as the same pressure difference as if your house is hit by a 20-mile-an-hour wind. So you're basically testing how your house performs when it's in a 20-mile-an-hour wind to see how leaky that house. And the lower the number, the less air leaks. In colder climates in the U.S. right now, the requirement is actually at 3 air changes an hour, so it's significantly less than the 5. But for a warmer climate, reduced air leakage house does not pay as big of dividends as a colder climate, so that's why a little more relaxed air leakage requirement. So this again is another requirement for the building envelope for fully conditioned buildings.
And Eric,
yes.
Let me jump in there too. When Eric and I were doing our statewide training, people would ask, "You mean blower door is required for Hawaii?" Yes, it will be when the code comes in. And we discovered by just taking a poll of the audience, there are apparently 3 blower doors on Oahu, 1 on Maui, and I think it was 2 on the Big Island. So they do exist. So this may be a growth area when the code does kick in.
Yes, and we're seeing that actually around the U.S. right now, because there's obviously areas in the country that don't have access to or ready access to equipment. So it's kind of a chicken and egg scenario. And if the code comes in and requires it, then people will they will buy blower doors and learn how to use them to be able to fill the need. So anyway, stay tuned for that. And the industry, as Howard has said, this could definitely be a growth industry. Last but not least, for the building envelope requirements is a requirement for IECC rated airtight recessed can lights. These are great thermal chimneys if they're not airtight. So any warm air you have up in your attic when you're trying to cool your house will come down inside the house, because air goes from hot to cold. So if my inside of my residence is cool and the the attic is very hot, the temperature drive is going to be from that hot attic into the house, and so you're going to get a lot of air leakage into the house. So if you can seal off your can lights as best possible, you're going to reduce the amount of air leakage that comes into your house and keep your house more comfortable. If your house is more comfortable, then the occupant won't run the air conditioner as much, and they actually end up saving energy. And there's some homes, at least built here on the mainland, that the entire ceiling is cottage cheesed with recessed can lights. It's kind of the lighting of choice. So these recessed cans, the IC rated airtight cans, the IC rating means rated for insulation contact, so you can insulate around them. And the airtight means that there's a certain amount of air leakage, but not very much air leakage for each of the can lights. So you can insulate around it and reduce the air infiltration from those cans. So that's the last slide for the building envelope. Now let's go ahead and start talking about what we're considering systems. And a system is going to be your cooling system and your water heating system. These are the two primary systems in a house that the code focuses on. And we're not going to get into all the details of water heating, but just kind of some of the major ones that we feel are really going to save energy. But first, we're going to talk a little bit about mechanical. And when you look at an air conditioning system, if you have a standard ducted system, kind of the weakest link in the chain is your ducts and sealing your ductwork. If your ducts leak, you can actually cause pressurization or depressurization in the house, which can actually increase infiltration because if you have a house, part of your house underneath the negative pressure, it's actually going to want to suck air in. And so that actually increases infiltration, and you can actually increase the air conditioning load on your house. So there's a lot of energy savings in sealing your ductwork, and then if you have ducts in what we consider unconditioned space, this is going to be up in an attic assembly, maybe it's in a garage, or it's anywhere that's basically outside of the space you're cooling. That's unconditioned space. All those ducts have to be tested using what we're calling a duct blaster test. And you're essentially testing how leaky your ducts are. So the lower the number, the better. And the metric you're using is at 4 cubic feet per minute per 100 square feet of conditioned floor area. So it's similar to envelope leakage when we test on that, except this is essentially you're pressurizing your ducts and you're determining how leaky your ducts are. And if your ducts are very tight, you actually have a nice system and it can comply with the code. And again, when Howard and I talked about this during our training swing in November, I don't know that we heard of too many duct blaster tests. Did we, Howard, when we brought this up?
No, some of the production builders on the upper plains test 1 out of every 7 homes, and they regard that as adequate testing.
Okay, great. So now if I have a ductless system or a mini split, whatever you want to call it, then there's no ducts to test and you're exempt from this requirement because essentially everything already is in conditioned space. So this is only for a ducted system when the ducts are actually outside of conditioned space. So Howard, I'm going to turn this over to you to talk about solar water heating.
Yeah, we decided that solar water heating was so important that we would put it right into the code. As the law stands right now, there's the energy code on the one hand and the solar water heating requirement on the other. But we wanted to put it right there. Why? Because there's probably over 100,000 solar water heaters in the small state of Hawaii. And if you track electricity use, and especially peak demand use in Hawaii over the last 15, 20 years, you will see that it is essentially flat. Even though there's lots and lots of new air conditioning going in, and there are new high-rises going in, there are new homes going in, why hasn't the demand been going up? One of the major reasons is solar water heating, and this has to do especially with peak demand. The utility has very low demand for electricity, say at 3 in the morning, then it begins to climb around 6, 7 in the morning and gets up to its afternoon peak, and then it climbs again at around 5 p.m., doesn't start going down till around 9:30. We're unique in the nation in that. Why is that? Number one, everybody is coming home from school or from work and turning on everything in the home. And number two, here's the kicker, all the tourists, and we have at least 200,000 tourists in our state at any given time. They're coming home or back to their hotels from the beach, from shopping, tours, whatever, and they're turning on everything in their hotel rooms, and then they're going to the restaurants and the bars, and those are going full tilt, and the combined effect is an evening peak. Now enter solar water heating. What happens when all those people come to their homes? The water heating goes, the demand for water heating increases terrifically. People get into the shower, washing dishes, so forth. But they have a battery in their home called a 80-gallon or 120-gallon tank of hot water. The increased demand on the water, the electric utility is zero because all the hot water is just sitting there. So this, from that standpoint, and achieving the Hawaii Clean Energy Initiative, solar water heating is ideal. And that's why it's in the code. And it could be expensive, except that you have a rebate from Hawaii Energy and federal tax credit plus state tax credit. Turns out to be a very, very good deal indeed. If you don't want the solar water heating, you do have the option of instant on gas heating. And the reason that's in there is that the gas heaters do not consume any additional electricity. So we're protecting the load there. So that's it for solar water heating. And electrical power and lighting systems, again, the more efficient the equipment that is in the house due to the more efficient envelope, the less demand for power there is, and the wires can be size smaller than would otherwise be the case. Little cost savings there. But let's get in specifically to lighting. And we have a photo here of CFLs, compact fluorescent. Actually, those are beginning to go the way of the dinosaurs. You heard it from me first. LED lighting is coming on very, 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 very rapidly. It's already accounting for 15% of all lighting sales, and that number will go up exponentially. Why? Compact fluorescent lamps have mercury in them, as do linear fluorescent lamps, and mercury is not good. You break a compact fluorescent in your home, you better get yourself out and the kids out and the dog out, because the mercury vaporizes and does bad things to the body. Plus, the CFLs just don't perform as well as the new LEDs. LED technology is improving just hand over fist. I hear tales of LEDs in the laboratory reaching 200 lumens per watt, which is 2, 3, 4, 5 times as much as your standard compact fluorescents do these days. Plus, LEDs used to be expensive. They are going down, down, down in cost as mass production sets in. Plus, Hawaii Energy is doing a lot to subsidize the cost of these lamps so that you can go to a big box store and buy one for $4.50 or $5. Not a bad deal, considering that they last, even the little ones, at least 25,000 burning hours. That translates into years and years. There are claims of burning up to 100,000 hours. And finally, an objection to LEDs is, oh, they're so glary, they're so ghost-like. Well, that used to be the case, but now, as the technology improves, you can mix the red, blue, green, the 3 primary colors, any way you want. The manufacturer can, and produce any color temperature light you want, all the way from very warm to very cool. So all of which is to say that this lighting requirement here is already outdated. It's almost automatic that you will have LEDs in new applications. So this is a very, very easy requirement to meet at the moment. Next slide, please. And ceiling fans. Ceiling fans work beautifully in Hawaii because our benign climate results in a temperature differential of, say, your outdoor ambient air versus your cooler indoor air of as little as 10 degrees, or if you have the ambient temperature coming in, say 85 degrees, a ceiling fan will reduce your perceived comfort by 5 degrees on slow speed up to 12 degrees on high speed. And given our mild climate, that makes all the difference in the world. You are very comfortable under a ceiling fan, and it consumes, I think it's as little as 1/20th as much energy as does an air conditioning system. So it's a great way to keep naturally cool and keep dollars in your pocket. And again, that is mandatory for the new code. If not installing the fan, then at least installing a rough-in so that you have a little plug in each bedroom and the larger room, so that when the new occupant decides to install the fan, the electrician just removes the plug, there's the wires, and he installs a fan very, very easily. Next slide, please. And simulated performance alternative. Were you going to cover this, Eric? Or
I can cover this, Howard.
You're
Okay.
covering it. Yep,
Yeah,
yep.
so
Okay.
great. So we've, throughout this webinar right now, we've been focused on prescriptive requirements of the code for the building envelope. Again, there's no trade-offs except for our points option. So we do have a prescriptive trade-off there, but everything is fairly prescriptive. And now there's another approach in the code we talked briefly about at the beginning of the webinar, which is a simulated performance alternative. And this is essentially taking your unique design. For example, if you have something special that doesn't fit neatly into the prescriptive approach and the point options, you're not getting the trade-offs that you need there for some unique building assemblies that you're trying to build, you can always do a computer simulation on the building. And essentially the software uses Hawaii weather data. It takes your building exactly how you're planning on building that building, runs it through a computer simulation, and models heating, well, actually not heating, but mostly cooling, lighting, water heating loads for a 1 year period of time, applies the Hawaii weather data to that, and it comes up with how much it costs to, in this case, cool your home annually. And then you take your proposed house, and internally in the software, it applies the minimum code requirements that we just talked about to your house. So let's, for example, it'll apply minimum wall insulation, roof insulation, floor insulation. There isn't any required in this particular climate zone, but it basically takes the prescriptive requirements and applies this to your house. So you have a minimally code compliant house, models that, determines the energy use of that home over a 1 year period of time. And as long as your proposed house uses the same amount or less energy as a minimally code compliant building, you've complied with the code. This right now is actually being used quite a bit in the mainland, in areas where there's consulting companies that can actually do this kind of work. The difference between the mainland code and what you currently have in Hawaii is the ability to do equipment efficiency trade-offs. So if I wanted to put in a high SEER air conditioner, let's say an 18 SEER air conditioner, and with minimum being a 14 SEER right now, I can actually use that increased efficiency to trade off against efficiencies in the building envelope. So maybe reduce my wall insulation or my roof insulation. So it gives me the ability to trade off higher efficiency heating or cooling equipment against envelope efficiencies. And again, Hawaii right now is the only state that actually has the ability to do this from a code standpoint. So this is an option. It's it's a viable option. You just need to find consultants that understand how the software works, because it's like any other piece of software. You have to understand how the programs work and things like that. But it's definitely a viable option to be used if other options don't work for you from a prescriptive and points option trade-off approach. So with that, Howard, I'm going to put up the question slide, because that's the end of the content. And if you have any questions that you'd like to ask, please email it to this to the address
on your screen.
Thank you. Yes, I'm drawing a blank here. It's getting late in the day. Idaho time. So, Jolynn Green at cadmusgroup.com. Again, it's Jolynn Green at cadmusgroup.com. So please go ahead and email your questions, and we'll go ahead and get those answered. I'm gonna start off with a couple of questions right off the bat here, dealing with existing buildings, Howard. And one of them is. I may have missed this, but does this code only apply to new construction, but does it apply to new construction and renovations? So how does this code apply?
There is, in the 2015, a whole new section called Existing Buildings, and the code is always applied to existing buildings, but now this has its own category, and there are more requirements, and our experience to date shows that by far the most interesting of those requirements is in re-roofing, where the mainland code says that if you re-roof down to the sheathing, and the sheathing is generally that plywood slab that holds everything up, and there is no insulation, you must insulate before putting the new membrane on the roof. I presented this to the Hawaii Roofing Association, and to a man, they said this will double the cost of re-roofing, not a desirable option. So I sat down with some of them, and we came up with a proposed alternative to that, an amendment to that, which I'm going to propose to the counties when they go through the adoption process that they use. And the new amendment says you shall do two of the following. Number one, have a reflective roof. Number two, have radiant barrier. And number three, have really good attic ventilation. And the roofers said, yes, this is the type of thing we do as standard practice anyway, so this is what should go into the code. It will significantly reduce the heat coming into the interior at a very, very nominal cost. So that is the main way that the existing building is affecting this code here.
Okay, great. So I've got another question that's dealing with existing too, and I'll throw this one out there. How does the code and air sealing, basically, if I have an existing unconditioned house and I want to install air conditioning on that house, what do I need to do from a code standpoint? Do I need to comply with the entire code, or how do I deal with that? So I'm gonna since you're talking about existing right now, Howard, I'm gonna throw this one out to you too. So
okay, yes, if you shift from unconditioned to conditioned, that new conditioned space must comply with the code. You need to do roof insulation, wall insulation, or it'll apply to the envelope section of the code. You must do roof insulation, wall insulation, and have high performance windows. And that can be an expensive chore, except that you do have the options that I was mentioning. You can do reflective roof, radiant barriers, attic cooling, and incidentally, we were talking about SHGC, solar heat gain coefficient of windows. There are window films that can go over existing glass and achieve the same effect, and you still have a good view of the outdoors. And then you can, in addition to putting some wall insulation in, do a projection factor over the walls or have a reflective wall as well. But you do need to bring the envelope up to code, and if you're air conditioning, you need to, that new air conditioner has to have the proper seasonal energy efficiency rating, which at the moment is 14. I don't think you can buy anything less than 14 on the market now anyway.
Right. Yeah.
Anything to add to that?
Well, the other option you have too, and we just spent our last webinar this, Howard, was that you can always only, maybe condition part of the house, for example. And so then you can actually use the tropical zone requirements and get by with with upgrading a little bit less of the house, and the requirements aren't quite as onerous. But that's certainly an option available to you. And so you don't have to, if you're fully conditioning, so you're putting air conditioning in every single room, then absolutely you're required to comply with the code. And if the system is ducted, then you also have to do a duct blaster test for duct leakage and that type of thing. But if you decide that maybe you can live with only a few cooling just a few rooms, then you maybe only have to worry about bringing it up to the tropical zone requirements, and so it's a little bit easier, a little bit a few less requirements. But so I was just thinking about that as you were talking, Howard, that might be an option. So
and let me tell a specific story just in case people are saying, well, that's an onerous requirement. We had somebody joined our energy office some years ago from Wisconsin, and he brought with him a pregnant wife, and they moved into an uninsulated home that had no shading, and she very quickly became very uncomfortable in the home. I mean, she is from Wisconsin, not used to the heat. So they put in some window air conditioners, and she found herself cranking the window air conditioners up to absolute maximum and getting blasts of cold air from different angles while feeling radiant heat from other angles. She was not happy, and she threatened to move back to Wisconsin, but the solution was found in putting radiant barriers, and this was without a permit, it was just done, putting radiant barriers through all the walls and in the ceilings. Instantly, the home cooled way, way down. She was able to turn the air conditioners down to lowest setting, be very comfortable, and she stayed in Hawaii. So that's why when you're shifting from non-conditioned to air-conditioned, you do want to take measures.
Great. Okay. Sounds like a great solution. So I'm going to have one more question here for basically existing buildings, and then we'll go ahead and wrap this up. If I have a single wall construction home and I want to fully air condition it, how do I insulate that wall? What are some of my options on that?
Well, obviously, R13, interior insulation. And then you ask yourself, well, if it's single wall, don't I have to put studs in to get the say fiberglass insulation in there? Absolutely. Or there are foam applications where you don't need as much thickness. You have open foam and closed foam. Closed foam requiring the least amount of space. That would be another option. And then the way to keep the walls cool again is through a good projection factor or a reflective wall. And more to that, Eric?
I was just thinking, getting back to our tropical home discussion on the earlier webinar, is that walls aren't required to be insulated from that standpoint. So I guess technically you could only condition part of that building and call it a tropical zone house and not have to worry about insulating walls. I mean, what we found in our analysis is that insulation of walls makes sense. Actually, even in tropical zone requirements, insulation in the walls do make a lot of sense, and there's quite a bit of energy savings. It doesn't make sense to put foam on the outside, primarily because if the stud cavities are already insulated. But for single wall construction, this is always a problem. I like the option of shading the walls because most of your loads on that wall are solar loads. So shading the walls make a lot of sense. But other than that, that's about all I can think of for this particular wall insulation requirement. We do have one more question that just came in that's being printed out right now. So Howard, do you have any other options for insulating those walls, or we kind of ran the
Yep,
gamut on that?
we've looked at it long and hard, and we've covered all the bases here.
Okay. The other questions that actually came in on the tropical zone requirements dealt with insulation placement in the attic assembly. Oh, here's a great question. I can bring that what I was going to say later. Where walls or other elements are exempt or being swapped in a point system, can ResCheck be used, placing a minimally complying insulation or solar heat gain coefficient, for example, to nullify the element of the envelope and demonstrate compliance with the remaining whole if ResCheck shows a percentage better result? So let me actually, I think I can address this one because we had a similar question that came to Howard and I a couple of weeks ago concerning the use of ResCheck in general in Hawaii. Right now, the U.S. Department of Energy ResCheck software is not designed around the modifications that were made in the Hawaii code. So if you get in there, there's no options for our points options, for example, no trade-offs for reflective surfaces on exterior walls. So those are specific just to the state of Hawaii. You can, though, if you want to be conservative, I mean that you're going to actually comply with a more stringent requirement. You can use ResCheck to comply with Hawaii's code for the building envelope. It's going to be certainly more restrictive than you currently have right now in the code. Wall insulation levels will be higher, for example. The glass will be about the same. Roof ceiling insulation still about an R30, so it looks at that. But there's again, for metal stud in particular, you're not going to go ahead and get the trade-offs that you would using the points option right now, because for metal stud wall systems, you are essentially going to have to you're going to be compared against a building that has foam board insulation on the outside of the wall system. So you can use ResCheck now, but again, you're not going to get the trade-offs and the credits that are currently built into Hawaii's code because the ResCheck really reflects the way the code is here on the mainland and not in Hawaii. So do you want to add to that, Howard, or did I?
Nope, that is comprehensive indeed.
Okay, I thought I might have confused everyone. So anyway, that is the last question that I have.
Can you put my final slide up there for my email address?
It's up there, Howard, right now. So
Yep. Okay. I'm the person to ask further questions of.
So
and that does it for us. Tomorrow we will have at 11 o'clock the commercial envelope, and then the next day commercial HVAC, the final day commercial lighting and electrical.
Great. And with that, let's call it a day. Thank you very much for participating in the webinar, and we look forward to your participation in future webinars. Thank you.
Absolutely. Thank you, and aloha.